Hi there YouTube, welcome to our as yet unnamed math series. But I'm not really worried about the name at the moment.
That's a lie, I'm actually really worried about that.
Next couple videos are going to be over conic sections, and for today we're going to talk about parabolas. Let's consult the math desk.
The math desk. Much better. And so, what the crap are conic sections? Basically, if you take a cone and slice it up into different cross-sections, you get different shapes that can be described algebraically. While most people picture cones as pointy shapes used for highway construction or hold ice cream or... Cones in this context actually look like two cones, one balanced atop the other. Now, if I were to slice through this cone exactly parallel to the base, or just look at the base itself because I'm lazy, I would get a cross-section that looks like a circle. If I were to make the cut at a slight angle, I get an ellipse, which looks like an oval, or a stretched out circle. If I make a cut perpendicular to the base, I get a hyperbola. And if I make an oblique cut, I get a parabola. The parabola has a couple different forms and definitions, some of which you probably already know. It is a quadratic function, that is, it has an x squared as its highest power term. You've probably seen it in two forms, ax squared plus bx plus c, which you use for the quadratic formula, and y equals x minus h squared plus k, which is more helpful for graphing since it gives you the position of the vertex. That is, either the peak or the low point, depending on whether it opens up or down, is always at the point h, k. Also, sleeping parabolas, or parabolas that open up horizontally, have the equations x equals ay squared plus by plus c, and x equals a times y minus k squared plus h. They open to the right if a is positive, and open to the left if a is negative.
A lot of the work you do with conic sections is identifying which of the four types the equation is. That is, a parabola, circle, ellipse, hyperbola, one of those four. And then you take the equation you're given and rewrite it or modify it into its standard form to find its defining characteristics. Now, we'll get to that last part in a minute, but first we need to know how to get back and forth between these functions. And that requires knowing how to complete the square.
Completing the square takes a lot of backwards thinking, so bear with me a second as I go through the opposite or inverse of completing the square, expanding and simplifying. Let's say you have a parabola in graphing form, y equals x plus 3 squared plus 4, and you want to expand that into the other form so you could plug it, say, into the quadratic formula. Following the order of operations, you would raise the x plus 3 to the second power. Now, I did this with a generic rectangle, not to be confused with the name brand rectangle. You can multiply it out however you want. No matter what you do, x plus 3 squared is x squared plus 6x plus 9. Now, take a look at this and see the pattern. You have the x squared. The coefficient is twice as much as the number back in the parentheses, and the constant is this number squared. This is true for any x plus h squared, something we can prove using the generic rectangle, or even Pascal's triangle for expanding binomials. But that's another show. Anyway, after that it's pretty smooth sailing. Now you just add 4 to the 9 you get from expanding, and you're done. Y equals x squared plus 6x plus 13. Now completing the square is very similar, only it works backwards. Let's take the equation from last time. First of all, we group every term with an x together inside parentheses. Now we want to find a form of x plus something squared that will give us what is inside the parentheses. To get the x squared plus 6x, we're going to have x plus half of 6 squared, because we remember from a minute ago that whatever number is added to x before it is squared, the coefficient will be twice that. So in this case, to get the terms x squared plus 6x, we're going to write it as x plus 3 squared. Unfortunately, x plus 3 squared isn't just x squared plus 6x. It's x squared plus 6x plus 9, because you remember when you expand it, you also have the 3 squared added to it. Since you accidentally added 9 too many with your x plus 3 squared, you're going to have to subtract it from the 13 on the outside. 13 minus 9 is 4, so your final equation is y equals x plus 3 squared plus 4. Look familiar? Just to make sure we cover all our bases, let's do one more. Let's say you have the equation x equals 4y squared plus 8y plus 3. Complete the square to find this parabola in graphing form. Again, you would group together the terms with variables, in this case y, and leave the 3 by itself.
All by myself. Other me, we don't have time for this. Plus, it's probably copyrighted.
Once the variables are grouped together, we can complete the square, right? Not so fast. Our trick with y plus half the coefficient only works with 1y squared, but this one has 4. We're going to have to factor out the 4 first to make it a single y squared. Now, factoring is kind of like the distributive property, only backwards. So in this case, we'd have to think, what would 4 have to be multiplied by to get 4y squared plus 8y? Well, 4 times y squared plus 2y equals that. Note that basically, you have divided every term of this by 4, and then brought the 4 back outside. If that's confusing to you, try distributing the 4 back into 4 times y squared plus 2y, and you get 4y squared plus 8y. That's all you're doing, only backwards. Every time you do this, you're going to divide the original terms by the number next to the x or y squared, and then instead bring the 4 back out front. This is called factoring, and it will be your best friend. I thought I was your best friend!
Yeah, no. No.
Alright, so we just factored out a 4 from the 4y squared plus 8y to get 4y squared plus 2y, and then plus the 3. Now we can complete the square. Half of 2 is 1, so we replace y squared plus 2y with y plus 1 squared. Now, with that, we will get y squared plus 2y plus 1. Keeping in mind, though, this is also being multiplied by the 4, so we will not have 1 too many, but 4 too many. And so we're going to need to subtract 4 from the 3, which gives us a final equation of 4 times y plus 1 squared minus 1. Since this has an x equals, we know it's a sleeping parabola. The positive 4 tells us it's opening to the right, with a growth factor of 4, and the center would be at -1, -1, if we look at the standard graphing form for sleeping parabolas.
A lot to take in, right? The nice thing about conic sections, though, is that you basically do the same thing every time. So let's just run through the steps one more time really quickly. Make sure you get it down.
First, group together anything with a variable inside the parentheses. Factor out whatever number is next to the x or the y squared. Complete the square by writing it as x or y plus half the coefficient of the x, then subtract the extra, which is going to be the multiplier times whatever number is in here squared. Then subtract this from the constant, and you're done. Graphing form achieved.
Speaking of achievements, this would probably be a good time to save your game, so to speak, because I have one more thing to cover, and that is the characteristics of a parabola.
Other than being a quadratic function, a parabola is defined as being equidistant to a point called the focus and a line called the directrix. Did I lose you? Here's all that means. If we draw a true parabola with its focus and directrix, every point along the parabola is the same distance away from its focus as it is from its directrix.
The important thing to keep in mind here is the definition and what it means. Another note is that parabolic surfaces reflect energy coming in towards it to a single point called a focal point, also known as the focus. This is why everything from satellite dishes to solar cookers are made out of parabolic mirrors. This also makes it very important to know where that focal point is. Otherwise, you won't know where to put the receiver or where to put your food to cook in the solar cooker. And if you don't know that, how are you ever going to watch How I Met Your Mother while munching on s'mores?
There are a lot of complicated ways to find where the focus and the directrix are, but the easiest way to put it is that they are both directly in line with a vertex. According to the definition of a parabola, the directrix is the same distance away from the vertex as the focus is. And these 3 points form a straight vertical line, or horizontal if it's a sweeping parabola. For now, we will call this distance, or this distance, because they're the same, P. So for any parabola that opens up with a vertex at h, k, the focus is at h, same x point, but the y point is k plus p. The directrix is going to be y equals k minus p. So the y subtracting this distance. If it opens down, the directrix is above and the focus is below. If it is a sleeping parabola, the focus is inside the parabola and the directrix is beside it. To find this distance p, we take the growth factor of our graphing equation, that is, the a of our a times x minus h plus k. The easiest way to find p is to remember that 1 over 4p equals a. So, if your equation is y equals 4 times x minus 2 plus 3, you set 4 equal to 1 over 4p. Some algebra will tell you that p would have to equal 1/16. Since the equation tells us a vertex is at 2, 3, the focus would be at 2, 3 and 1/16, and the directrix would be at y equals 2 and 15/16, as shown by the math here.
With any luck, that's all you'll ever need to know about parabolas. You know, except for playing Angry Birds, which is fun. But I'm actually saving those for a calculus video. Now, if any of this moved too fast for you, the joy about this is that you can rewind it and watch it again. And if you need any further guidance, I'll put links down below. Thank you for watching, and take care.